name is Gabriel Perry, and I'm with Idea Labs at Brigham Young University. I'd first like to thank my sponsors, the U.S. Department of Energy, Achilles Heel Technologies, which specializes in improving robustness of cyber-physical critical infrastructure. I'd like to thank the CDC for allowing me to present. I'd like to thank my family in California, Utah, and Arizona, and especially my wife who can't be here today. So the first question that I want to pose is why do I have another matrix inverse algorithm when there are already so many out there? So most of the time when you perform a matrix inverse, you're trying to solve a least squares equation or a similar system of equations, which requires you to compute an entire row or column at least of a matrix. But we had an application in our lab where we only were necessarily interested in one entry at a time. So we asked the question, how can we invert a single entry of the matrix or get one entry of the inverse as quickly as possible? And Mason's gain formula required using determinants, which were very costly for large matrices. So this led us, this was the application that we had in our lab. We have a model in our lab called the dynamical structure function, which is basically an abstraction of systems where we have some set of inputs and some set of measured states, but we don't care about the hidden states. And this allows us to model the signal structure, so the interconnection between the measured states in such a way that an attack, which directly writes to the measured states, can be propagated, and we can simulate the effect of that signal on the other measured states. And basically what the problem boiled down to was to measure the gain between these signals. We wanted to take the element-wise invert, or the element-wise norm of this inverse matrix. And because it's element-wise, that led us to this question of how can we just get away with getting one entry from the inverse matrix. Our work, of course, because it's systems, will be over rational polynomials, but for the purpose of this presentation, I'm going to work over the reals for simplicity. First, I want to introduce the reduction that we used to get to the algorithm. So first, given a matrix, which the conditions on what kinds of matrices our method works is in the paper. But this is a simple visual example. We construct a new matrix according to the equation given there, which is pretty simple. We interpret it as the adjacency matrix of a graph, a flow graph, where the flow between nodes, or the column edge indices, is given by the entries or the labels on the edges. So with this new graph, the essential question, which ends up helping us compute this matrix inverse, was what is the net flow? So the net flow is the sum of all path contributions. Paths of length 0 are the identity known to itself. Paths of length 1 are single edge paths, and the flow is given by the label on the edge. And we'll continue this pattern, and we'll end up building up this power series. Just to illustrate further, this is the second term, so all paths of length 2 edges is given by the square of that matrix Q. And we can see in this second column, the outgoing edges from 2 do include a path back to 2 along an edge with flow EB, and then another path to 4 with flow C times D. And the net flow is going to be the sum of all these contributions. For example, from 2 to 3, we have an edge with weight E, and then we have the cycle going back from E, B, E, but we could have also gone around C, D, A to get to 3, then we can go around any number of times. We sum all of them, and we get an answer equivalent to Mason's gain formula, but you'll notice that there's a determinant in that denominator, which for large matrices, we don't want to compute the determinant. So this will give us this power series, which for sufficiently small norm Q converges to this expression, which is the inverse of the matrix that we want to analyze. Summing the terms sequentially with the path length 0, 1, 2, etc., this discovers these flow paths in sort of a breadth first search. And the result from doing it this way is not surprising. This is just a Taylor series expanding about the identity. But we could ask the question, what about if we use other graph searches, what's going to happen? So some existing algorithms based on a similar approach, Floyd-Warshall, we applied that search algorithm, we'll actually get Gaussian elimination. The breadth first search we just discussed, and then a depth first search without repeat nodes along the path will give us Mason's gain formula. Another assumption that we made, because Q has to have this norm so that it converges less than 1, we can assume that we can truncate paths that dip below some threshold because all of the entries in the matrix are less than 1. So the labels on all the edges allow the paths to monotonically decay. And then because we're able to cut off those paths, we can ignore entries in the matrix effectively during computation, restricting us to this horizon surrounding the nodes of interest. And then this allows us to read less data from memory and potentially use the memory hierarchy more efficiently. So the question then becomes, like, we want to make this horizon smaller so that we can use less memory. And then a nice little diagram showing the reduction. We reduced the matrix inverse problem to a graph search problem, searching for these flow paths and the computations necessary to find them. So the next question is, which algorithm are we going to apply to our specific use case? And I chose the bidirectional search. So just as a summary, here's the epsilon horizon with the power series that we just saw. So we go out to some threshold epsilon, and I'm going to call the number of the nodes that we had to fetch from memory, P. The bidirectional search expands those paths from both the source and the destination simultaneously. So that way we can get away with meeting in the middle, and overall we'll read asymptotically the square root of the number of entries that we would have had to read in the other method. So we can eliminate extraneous paths such as the one leading to node K, if we just want to compute between I and J. And we'll keep in mind that the root epsilon is larger because it's less than 1, and that larger thresholds lead to smaller horizons. So here's an overview of the algorithm that we had. So it's color-coded with the animation on the next slide. So the first stage is the focusing stage, where we compute those epsilon horizons using the same breadth first search that we had before with the Taylor series. But then once we use our weaker epsilon threshold, we can restrict our computation to within those horizons to continue through, and without loss of accuracy, we can just do the computation within that area of interest. So here's a nice little animation. The first step in the algorithm, we see we're computing these flow paths until we reach the weaker epsilon horizon around the sink, working backwards. And then we do the same thing around the source, working forwards, until we reach that threshold, and it's the square root threshold. And then what we do is we continue computation only using the columns that we earmarked as directly applicable to this entry of the matrix, of the inverse. So we continue those computations until we get our estimate for the net flow of the sum of all paths that have contribution greater than the original epsilon that we were shooting for. The matrix interpretation of what's going on in this algorithm is that that first stage essentially creates a rough estimate of the row where our entry of interest is with this weaker threshold root epsilon. And then when we expand around the source, we're getting a weak estimate of the column where our entry of interest is. And then when we finish off that computation, we take the weak estimate of the row, the weak estimate of the column, and we get a better estimate at their intersection, the one entry that we were most interested in. Here's the error plot for algorithms. The red is the original power series, where we didn't round. We only truncated the series after the norm of the next term dropped below epsilon. The black method was the same power series, but we rounded every entry that dropped below epsilon, so that introduced that horizon. And then the green is our method, which we see consistently, because this is a log plot, that constant distance is a factor of a half of the absolute error from the black method. But the time scale was not even comparable, because whereas our method and the black method ran very quickly within an order of less than a second for matrices this size. Bottleneck was the red, ran for on the order of minutes per data point, so very fast. Our methods. Here's some of the symbols from the paper. The threshold epsilon, the sparsity is the number of non-zero entries per column or the number of outgoing edges per node. And then a rho is the one norm, which is a bound, so that we get that convergence. The norm is less than 1. The number of nodes in a horizon, given a sparsity epsilon and spectral radius, is less than this bound. It's less than this bound. The exponential term is misleading because of the natural logarithms. It's actually roughly linear in each of those terms. And then here is the error. This is a conservative error. You'll notice that it's the norm of the entire column, not just of the entry. This was a little bit easier to compute. But it does put a bound on the absolute error of that column. You'll notice that it is sensitive to the conditioning, so the norm of that, the inverse of the matrix that we're shooting for, which, because we're computing an inverse, we would expect it to be sensitive to the conditioning of the matrix. And then we'll notice also over here, we get one term roughly for each phase of the algorithm, the focusing, the continuing, and then the truncation, the final truncation term. We'll also notice that as epsilon goes to 0, we don't round anything. So as expected, the error also goes to 0. And that happens because the epsilon terms dominate the natural log asymptotes. The error does actually go to 0 as we stop rounding. The number of flops required, we measured. Our method asymptotically was the same as using rounding, but did significantly better than the Taylor series without any rounding. The error we saw in the previous slide, our method was able to get that gain of half the absolute error. The number of columns fetched from memory, so this was where I mentioned the high memory hierarchy, we tried to use it better. So by restricting our computation to sort of those entries of interest, we were able to use the memory hierarchy a little bit more efficiently with having more cache hits. And then that, hopefully, even though it's the same number of flops, will lead to faster actual runtime on real hardware by using the memory hierarchy more intelligently. As far as future work, I had an idea a couple weeks ago to extend this to Monte Carlo tree search. It'd be a little bit stochastic. But you also get the benefit of a stop anytime algorithm. We could think of applying an A-star search, but this would require having some notion of a norm on your graph. Descaling, similar to what John Doyle did with the structured singular value, we could imagine extending the set of matrices that we can use this algorithm on by performing a diagonal scaling on each side of M to massage it into a form that we can use for this algorithm. Also, at this point, we throw away the computation of the row estimate. I could imagine a situation where we could use those flow numbers as part of the computation so that we don't have to repeat that computation. And then, of course, there's our goal application is to use this in the systems that we are analyzing, where these would be rational polynomial transfer functions, but there's some issues with doing this symbolically because it's just symbolic computation is hard.
Thank you for that. Do you have any questions for the speaker? Looks like you explained everything for everybody. Oh, got a question.
How big do the matrices usually have to be for this to be very much worth it?
So it depends on the sparsity. So if the sparsity is on order of the same matrix, for dense matrices, there's not really a gain because you're reading all the entries anyways. But for sparse matrices, it's approximately just the square root. I think the sparsity is about the square root of the size of the matrix. You start seeing significant gains. And then there was also, because of this sparsity, it actually didn't matter if you make the matrix larger. If you hold the sparsity constant, the graph sort of, you don't go far enough to see the new parts of the matrix. So performance actually levels off and it starts taking constant time.
All right, it's time to speak on once again.